Okay, so we are going to look at night exercise number 38, and it reads, the 100 kilogram block in the figure I've drawn takes 6 seconds to reach the floor after being released from rest. What is the mass of the block on the left? The pulley and the rope are frictionless. The ropes are frictionless. All right. And massless. That's what I'm trying to say. So what is the mass of the rope? The mass of the block on the left. That's what we're interested in determining. So that's what we're going to go after. When we think about masses, we might think about interactions and forces. And so let's do a force analysis of that mass on the left. And so if we look at a free body diagram of this mass, we see that we have the force of gravity acting down and the tension in the rope acting up. And if I want to determine the mass, I need to do a force analysis and think about Newton's second law. So I'm looking for this mass M. And I only have two forces acting in a single dimension, so I can just look at that vertical dimension, force number 1 and force number 2. Force 1 is minus mg, and force number 2 is the tension. Now, the sum of the forces in the vertical direction are equal to the mass times the acceleration in the vertical direction, and this mass is moving. So we have the tension minus mg is equal to the mass times the acceleration in the vertical direction. Well, I still want to determine the mass, so if I solve this equation, I bring mg, so tension is equal to the mass times the acceleration in the vertical direction, plus mg. The tension is equal to the mass times the acceleration in the vertical direction plus g, and I find that the mass is equal to the tension divided by the acceleration in the vertical direction plus g. So in order for me to get the mass of this object, I need the tension, and I also need the acceleration in the vertical direction. Well, what are those related to? Well, the tension is the tension in the rope. That might be related to the tension interacting with this block. The acceleration is the systems moving together. So the acceleration is the acceleration of the system, and I have some information about the object's motion. So I might want to look at either one of those options. So let's start with one. Let's start with the acceleration. Let's look at the acceleration of this object. All right, and I've already considered the direction of the acceleration here, so we want to keep that direction idea in mind. Okay, so what is the acceleration? Well, that's kinematics. That's looking at the motion. So my object now, whether it's of this object or of this object, the object, let's look at block B. We're going to analyze the motion of block B. This is my block B. And that motion starts when it's released, and it ends when it travels 1 meter. 1 meter. All right, so x initial, I have to set an origin, so I'll set my origin there. X initial, x final, v initial, v final, acceleration, and time. All right, so my initial position, I'm going to switch colors because that blue's not working so well, is 0. Final position, minus 1 meter. It travels that 1 meter. Initial velocity, and just keep in mind this does say it is released from rest, so it has an initial velocity of 0 meters per second. We don't know the acceleration, the final velocity. We don't know the acceleration. This object is not in free fall because it's interacting with something other than gravity. It's interacting with that rope. So it's not in free fall. So we don't know the acceleration. And it says the time is 6 seconds. All right. So we're interested in determining this acceleration. I have my initial final positions, my initial velocity, my time. I'm going to use this relationship. So x final minus 1.0, x initial is 0, v initial is 0 times 6, plus 1/2 the acceleration times 6 squared. So I have minus 1 is equal to, those terms both go away, 1/2 times 36 is 18, 6 squared is 36, yep. So 18, so I have 18 times A. The acceleration is 1 divided by 18 is 0.0, a little more space, 0.056 negative is equal to my acceleration. So this block is accelerating at negative 0.056. This block is accelerating down at negative 0.056. This block is accelerating up at 0.056. So this one's going down, that one's going up. So I have my acceleration value, the acceleration of block A, this is block A, is equal to 0.056 meters per second squared. So I have that value that I need. All right, now I need the tension T. So tension T, well, that is related to block B. So let's look at the forces on block B. So the forces on block B are the force of gravity of block B, which equals the mass of block B times G, and the tension T. And these are only acting in the vertical direction as well, so I can just look at my two verticals. So I have vertical dimension, force 1 and force 2. Force 1 is in minus mg. Force 2 is a positive tension. The sum of these forces vertically is equal to the mass times the vertical acceleration, which, I know. So I have minus mg, this is block B, times g, plus the tension equals the mass times the acceleration in the vertical direction of block B, which is given here. So I have the mass of block B is 100 minus 100 times 9.8 plus the tension is equal 100 times negative 0.056. Acceleration of block B is in fact negative. All right, so the tension then is equal to 100 times 9.8. I'm going to add that, good Lord, I can do that in my head, 980 minus 100 times 0.056, 5.6, could have also done that in my head, and 980 minus 5.6, the tension is equal to 974.4 newtons, 974.4 newtons. Now, this is a good spot to check. Does this make sense? If the tension in on block B was less than the force of gravity, then the block should accelerate in the downward direction, and it does. So it's less than the force of gravity. These are the only two forces acting on the block. That means the acceleration must be in the downward direction, so the tension must be less. So it's just sort of a good check because we're dealing with some directions, and sometimes we put them in explicitly, and sometimes we let them pop out. In this case, we put it in explicitly because I had calculated it. But if we didn't do it in that direction, that might end up getting a little confusing. So it's always good to stop and say, does this make sense? Should my acceleration have been negative? Yeah. Should my tension force be less than gravity? Yeah. So it's always good to do that sort of double checking. All right, so now I have the tension force in B, and which is what I needed to determine my mass. So I can use this and this to get my mass. So I'm just going to rewrite the equation. I don't like that blue. The mass was equal to the tension divided by the acceleration of block A plus the force plus G, 9.8. So I have 974.4. Acceleration of block A was 0.056 times G, or plus G, sorry, not times, plus 9.8. And that equals 974 divided by 0.056 plus 9.8, 98.9 kilograms. All right, does that make sense? Well, if this block weighed more than this block, then the machine would go that way. It doesn't, so we know it needs to weigh less. or have less mass, and therefore weigh less, have less mass, and in fact we do. So magnitudes, if we have a math mistake, that might exist, but in terms of what our values should be, it should make some sense. So that evaluation process is also a very helpful tool. All right, so how did we tackle this problem? Well, we went after what we wanted, the mass of block A. And the only way to get that is really through force analysis. Kinematics doesn't tell us anything about mass. And we realized what we needed. We needed the tension. Ooh, that was related to block B. And we needed the acceleration, also related to block B, but in dealing with motion and the motion information we had. All right, is this the exact order that you have to do these problems in? Not necessarily, but this is just one approach, letting the physics tell you what you need. All right, good job.